Hey guys, so in this video I'm going to be just covering over Newton's law of cooling. This is like usually an excellence level question in level 3 integration, and basically it Newton's law of cooling just states that the rate of change dt with respect to time of like a hot body is proportional to the difference between the temperature of the hot body and temperature of the surroundings, right? And so to complete the equation, we can say that the change in temperature with respect to time, or dt by dt, is equal to negative k bracket t minus t0, where t is the temperature of the hot body and T0 is the temperature of the surroundings. So wrong one. Cool. So basically now, why is it negative? It's negative because the this temperature, the temperature of your hot body, will decrease and it will approach the temperature of the surroundings. So if you graph it, the temperature of the hot body as a function of time, right? Then it will go like something like this, right? It will approach some like value that is the surroundings temperature, and basically to a state of like thermal equilibrium, right? And if you draw a tangent line at any point, you'll realize the gradient is negative, therefore the rate of change must be negative, right? And so to solve Newton's law of cooling, we can start by separating the variables, right? So if we take, we're going to divide both sides by t minus t0 and take this dt by to the other side. So we're going to get 1 over t minus t0 with respect to temperature is equal to negative k with respect to time, right? And now let's go ahead and actually integrate. Your next step is to integrate both sides, right? So integrating the left-hand side, we're going to get ln of t minus t0 is equal to negative k times t plus c, right? And then the next step is we're going to do e to the power of both sides, right? So this would cancel this out, and so we're going to get t minus t0 is equal to e to the power of negative kt plus c. Now, also, what you should recognize is that because if you have the same base and you can add powers, so we can actually break this up and write it as e to the power of negative kt times e to the power of c. Now, note that e is actually a constant. E is approximately equal to 2.71828, right? And c is just some number. So this entire term is just like some whole number, right? Not a whole number, it's just some number. So we can write t minus t0 is this, and then to make things simpler, we can just say like let some variable a, b, c, whatever you want to use. I'm just going to use lambda. So lambda e to the negative kt, where I'm going to say let lambda equal e to the power of c, right? And so t is equal to t0 plus lambda e to the negative kt. And so this is basically Newton's law of cooling. But you should remember that, this can come in like a couple different forms. And I'll go through like a question from the past paper today. but you can be asked to find several things from this question. So yeah, let's get right onto that practice question I've got. So this is from the 2018 integration paper, and this one is to do with the mass of a burning candle. Um, so the mass m grams of a burning candle T hours after it was first lit can be modeled by this differential equation, right? And so this means that when T equals 0, M is equal to 140, right? And then when T equals, because T is in hours, so when T equals 3, M would just be a half of 140, which is 70. And so we have to find when M equals 50, find T, right? So let's write down our differential equation. dm by dt is equal to negative k bracket m minus 10, right? And so separating our variables, dividing both sides by m minus 10, we're going to get 1 over m minus 10 with respect to mass is equal to negative k with respect to time. And now let's go ahead and integrate both sides. So same thing, ln of m minus 10 is just going to be negative kt plus c, right? And then e to the power of both sides. And we're going to get m minus 10 is equal to e to the negative kt times e to the power of c, right? And I'm just going to state that let lambda equal e to the power of c, right? And so m is equal to 10 plus lambda e to the minus k t. Sweet. Now what we can do is start to make the equation fit for whatever our scenario is. And so we're going to start by subbing in t equals 0 and m equals 140. So when t equals 0, m is equal to 140. And so 140 is equal to 10 plus lambda e to the negative k times 0, right? And so 130 is equal to lambda times e to the 0. Now e to the 0 is just 1, therefore 130 is lambda, which is the difference. So we can now write m is equal to 10 plus 130 e to the negative kt. Right, one variable down. Um, and let's go to our next point here. So when t equals 3, m equals 70. So when t equals 3, m equals 70 grams, right? So 70 is equal to 10 plus 130 e to the power of negative 3k. And we got to solve for k. So let's go ahead and write this out. So 130 e to the negative 3k is equal to 60. And so e to the negative 3k is going to be 60 over 130. Or could that be simplified? 6 over 13. So e to the negative 3k is equal to 6 over 13. And now let's go ahead and take the natural log of both sides. So negative 3 ln of both sides. So negative 3k is equal to ln of 6 on 13. Therefore, k is equal to 1, negative 1/3 ln of 6 on 13. And putting that in my calculator gives k to be 0.2577. Okay, now that's our k. Cool. That's quite a long working, so I think I'm going to bring some of it up over here. So let's rewrite our equation now. So m equals 10 plus 130 e to the power of negative 0.2577t. And so now what we need to do is solve for t. So since we know that m equals 50 grams, so we can just take this 10 to the other side and write 130 e to the negative 0.2577t is equal to 40. And so e to the negative 0.2577t is just going to be 4 on 13. And so taking the natural log of both sides once again, oh, sorry, that just froze for some reason. Anyways, so ln of 4 on 13 is this. And so we're going to get negative 0.2577 times time is ln of 4 on 13. So therefore t is going to be negative 1 on 0.2577 ln of 4 on 13. And so t is going to be putting that in my calculator, I get t equals 4.57 hours. And yeah, so that answers the question. The length of time, therefore, we can just write that. Therefore, it will take 4.57 hours for the handle mass to reduce to 50 grams. And yeah, so that's Newton's law of cooling. And yeah, I hope that helps. But yeah, thanks for watching.